It's a great pleasure to introduce Dr. Alex Gittens. He's assistant professor at the Rensselaer Polytechnic Institute. He got his PhD in applied math from Caltech, did some postdoc period at UC Berkeley, and then joined RPI. He's interested in large-scale machine learning and randomized numerical linear algebra. And he's going to talk about trading off accuracy for reduced computation in scientific computation.
Okay, thank you, Jawad, and thank you all for attending. So as Jawad mentioned, today I'm going to be talking about several works that I've done with my collaborators over the years, where the idea is that if we want to solve a problem to some medium accuracy, so this occurs a lot in machine learning, we can trade off the usual computational costs. We can reduce that by accepting some increase in our loss. And you should be able to control this in a principled way. And so I'm going to give several examples in different contexts. So I'm going to give one in tensor approximation, one in nonlinear clustering, and one in solving kernel problems. Okay, so we'll begin with just sort of a quick review of what sketching is to motivate it. So we're going to do this in the context of ridge regression. So we've all seen ridge regression before, I'm sure. So the idea is we want to solve some linear system, which may be inconsistent. So we add a L2 regularizer. So we want to solve this linear system with a prior that the coefficient should be kind of flat. So we know the optimal solution you get from ordinary least squares, and you have this term here that sort of makes your solution more or less independent of the data as I increase the regularization. And the cost of this is like the cost of taking a QR and then solving that triangular system. So it's ND squared. So throughout N is the number of rows in X here, and D is the number of columns in X. Oh, or that's a direct solve. And if you do an iterative solve, it's ND times T, where T is your number of iterations, which typically depends on something like the condition number of your system. Okay, so we're gonna specifically consider the case where we have an over-constrained system. Because here we're solving for a variable that just has D degrees of freedom, but we have many more than D constraints on this. And the issue is, if these constraints are all sort of nice, right? There could be a lot of constraints that don't matter at all, but let's say they all matter sort of equally, then we could imagine that we should be able to reduce to just order D constraints. That's how many we need to have a consistent linear system. So the question is, how can we exploit this insight to select just a part of the data so that we're solving a much smaller problem so that we can trade off between, as I said before, accuracy and computational costs. So we would expect, instead of having that dependence on N, we'd have a dependence on something closer to D if we did this in the correct way. Okay, so this is where sketching comes in. And the idea of sketching is we assume that we have a lot of data, but there's some sort of low rank structure or something that allows us to keep the same information in a much smaller amount of data. And here we're going to use linear sketching. And the idea is to replace your large matrix with a smaller one. And we're going to model this process as multiplying on the left-hand side by our sketching matrix S. So here S takes us from N dimensions to S dimensions, from N constraints to S constraints. And we could either be sampling, in which case S here looks like a subset of the columns of the identity, or we could be mixing these constraints and then selecting them. So this gives us a whole range of different ways of sketching, and they're motivated by different concerns. So obviously, if you wanted to do something that's completely data independent, you could do uniform sampling of our constraints. That may be a bad idea. For example, consider the case where a lot of the rows of X are 0. Then we don't have any information from those constraints. So uniform sampling might be a bad idea. Okay, so when we have a sparse X, uniform sampling is not a good idea. But if we do want to sample constraints, leverage score sampling is a type of importance distribution sampling. So you get an importance distribution over the rows, and then you can sample from those. And that works okay in the sparse setting as well. You can prove something about how many samples you need for each of these types of sketching. For leverage scores, you need much fewer than you do for uniform sampling. For uniform sampling, you could need to sample the entire matrix. And then if you're allowing yourself to mix and then sample your constraints, there's the Gaussian projection, which is literally just take a random Gaussian matrix and multiply your constraints by this Gaussian matrix to get a smaller set of constraints. So you're just mixing all of your constraints together randomly. And that also gives us, we need on the order of D constraints sampled. But the issue with Gaussians is that's expensive to multiply by a fully random dense matrix. So we've come up with a whole class of what's called fast randomized orthogonal transformations. And these take advantage of, say, for instance, the fact that we can apply FFTs fast. So we can apply these much faster than using a dense projection matrix. And then finally, there's something called count sketch, which allows us to work efficiently if X is sparse. A count sketch can be applied in time linear in the number of non-zeros. Okay, so there's a whole sort of spectrum of different conditions under which it makes sense to choose one or the other type of sketching. And sometimes it's possible and useful to provide guarantees that are independent of the particular sketch. Okay, so as I mentioned, some matrix sketching methods are more efficient than others. We want something that's lower than the cost of multiplying by a dense matrix. So leverage score sampling, for instance, can be done in near linear time in the size of your matrix. And the same thing for these subsampled randomized fast orthogonal transformations. Okay, so here's the idea of sketching. So we sketch the whole system. We leave the regularization alone, of course. And then this leads to our perturbed solution. And then, of course, you would like to guarantee something about the quality of this solution compared to if we had directly solved the ridge regression problem. Okay, but this is the goal, to get this nice, nearly square linear system because it's cheaper to solve. Okay, so the cost of this solve, remember before it was ND squared if we did a direct solver, now it's SD squared because we reduced using sketching. And then of course you have to account for the cost of sketching. So here are the type of guarantees that you can get. So if you use leverage score sampling, then like I said, you need basically order D samples. Epsilon here is your precision. Okay, and with those number of samples, you get this guarantee that the error of your sketch solution, so this is the objective here, our ridge regression objective, is only slightly larger than that of your optimal solution. And beta here, by the way, is a number that's less than 1, and it accounts for how as you increase the regularization parameter, your solution becomes less dependent on your data, so you can sample more aggressively, right? So as gamma goes up, that beta gets closer to 0, and you can sample less and less constraints. Now, uniform sampling can be very expensive because it depends on this thing called the row coherence of X. And in the worst case, your row coherence could be N over D. In which case, if you look at this thing, it's order N. So you have to sample everything. Okay. And the reason for this is that leverage sampling is adaptive to your data. Uniform sampling is not. Okay, so that's kind of the setup where we are. So these results here are taken from a paper where we also looked at, so this is from an optimization perspective, but you could also consider that your data is random, in which case then you could ask about the bias and the variance of these different types of sketches. Okay, so this is the optimization perspective. We're going to go with that throughout this talk. So the first application we're going to look at is using the sketching idea to speed up getting low rank decompositions of large tensors. Okay. Oh, by the way, if you have questions, feel free to ask as we're going along. So here we're taking a order 3 tensor. This can apply to higher order tensors as well. And our goal here is to learn factor matrices that explain each of the modes of this tensor. So you could think of A here as capturing what's going on in the columns of this tensor. Think of it as a basis. B is a basis for the row space of this tensor. And C is a basis for the third order mode of this tensor. And then here, think of each of A, B, and C has R columns. So we're looking for rank R bases, okay? And the AI, BI, and CI are just columns in these factor matrices. So this is sort of the analog of a rank 1 outer product. If this was a matrix, you would be saying, I want to approximate my matrix as a sum of rank 1 outer products. Here, this is the 3-dimensional analog. So we want to approximate my order 3 tensor as a sum of rank 1 outer products. Okay. And we write it in this notation. So again, the AIs are the columns of A, the BIs are the columns of B, and so on. And these are called our factor matrices. So our goal is to minimize the sum of squared errors in approximating our tensor by choosing our factor matrices A, B, and C appropriately. So this has a lot of motivations in data analysis and in data compression. So for instance, if you had a tensor data set that was actually low rank as a tensor, in this sense that there is some small r where x can be written in this way, then if you were to compress it by learning A, B, and C, you can save an exponential amount of space as opposed to if I turn that tensor into a matrix and then use the SVD to compress it, okay? So if your data is naturally tensorial, these tensor approximations are very useful. So here are our questions and our results. So there's 2 questions. One is we want to use sketching to speed up getting these decompositions. So how can we do that in a way that gives us a conversion algorithm? So it's been proposed to use sketching before. Different types of sketching have been proposed that are more efficient in the tensor setting, but the convergence of those algorithms was not shown before. And then the practical question is, how do we then choose these sketching rates to ensure convergence in practice? Okay, so to answer these questions, we have some theory on how to choose the sketching rates, given some oracle about quantities that we don't actually have access to. We can come up with a conversion algorithm if we choose our sketching based on those quantities. And then in practice, we have an online heuristic for choosing these sketching rates that adapts and empirically converges faster than other methods of choosing the sketching rate. So here's the classic algorithm for getting these canonical polyadic decompositions. So we can pose this as a Gauss-Seidel type problem. So we update A, fix B and C. We fix A and B, or sorry, we fix A and C and then update B. We fix A and B and then update C. And this gives us a sequence of low rank approximations for which it's clear that the approximation error has to be non-increasing just by construction. And then under reasonable conditions, you can show that these converge in the sense of they reach a critical point of the objective, which is all we can ask for. Okay, so how do we make the connection to sketching? Well, the key observation is that the Frobenius norm doesn't care about the shape of the tensor. So in particular, we can flatten these tensors out into matrices. So here's an example of a order 3 tensor. And if we flatten it into the first mode, we just construct this matrix whose columns are all the columns of X. If we flatten it into the second mode, we construct this matrix whose columns are all the rows of X. If we flatten it into the third mode, we construct this matrix whose columns are all of the mode 3 fibers of our tensor. Okay, so if we reshape these CPD subproblems by matricizing them, we get these linear systems here. So this operation here is the column-wise Cattry-Rao product. So remember, B and C each have R columns. B has J rows, C has K rows. When I take their Cattry-Rao product, I get a matrix that also has R columns, but now it's very tall. So it's J by K. So this is a very tall system, which means we're in the setting where sketching makes sense. Okay, so these are 3 least square systems that we're going to solve in sequence. And like I said, they're over constrained. So the Cattry-Rao product of B and C has JK rows. Okay, so this is the transpose. Similarly, when I matricize X, it has JK, JK columns. All right, so now just looking at this, you can see that every row of A has only R degrees of freedom, and it's constrained by JK equation. So there's just many more constraints than there are degrees of freedom. And the same thing happens for the other factors. So it's natural to consider sketching this problem by selecting subsets of the constraints at every iteration. So every time we have to solve a linear system, we select a new subset of the constraints. Okay, so of course, this is a pretty natural idea. So there have been prior sketched CPD algorithms, and they provide guarantees like the kind that we saw sort of in the introduction. So if I sketch my system, then the update that I get solves that system almost as well as if I had just directly solved my system without any dimensionality reduction. But the issue with this is that potentially that error could actually be increasing, right? Because slightly larger than optimal could be larger than my previous error. So my error is no longer non-increasing, and showing convergence hasn't been done before. Okay, so that's one issue. Another is that these prior algorithms, because they kind of focused on this setting, getting this kind of guarantee, they didn't really address the problem of choosing sketching rates to ensure that you're converging. Okay, so in particular, hyperparameter selection is a problem that wasn't addressed, where the hyperparameter here is the sketching rate. Okay, also, they're vulnerable to swamping that's caused by the fact that these linear systems can be ill-conditioned. Like if the factors in A, if the columns are nearly linearly dependent, then you get some ill-conditioned systems. Same for B and C. So here's an example of swamping. So this is if you did a naive CPD ALS solve, and then here we inserted some proximal regularization that just says keep each iterate close to the previous value of your factor matrix. And we can see that that helps mitigate swamping because it basically makes your solve strongly convex. Okay, so here is regularized ALS, where we added this proximal regularizations. The nice thing about this is that the critical points of this system are the same as for ALS. Okay, also we observed in some previous work that adding that proximal regularization helps mitigate any error you might get from sketching. So here we're plotting the error. So this is just the least squares error ratio of algorithms compared to standard ALS. And we're also plotting the ratio of their run times. So this green area is where the error is lower than standard ALS and the runtime is less than standard ALS. So that's kind of the goal. And you can see here that combining proximal algorithms with sketching takes us into that nice regime. Okay, so we want to say something about this. So here's the meta algorithm we're going to look at. So we're going to sketch our systems here, and we're going to use proximal regularization. So the first observation is that, by doing some careful analysis, you can show that the error decreases by a fraction of the maximal possible decrease for each of these solves. Okay, so here I replace the Caturel product with the system matrix M, just to make things easier, and I'm just considering the update for A. So let R be our residual. So this is the error when we use A, B, and C to approximate X. So the best that we could hope for by updating A, by solving this, is to capture the projection of our residual onto that system matrix. That's the best we could hope to decrease the error by, because any part of the residual that's not in the system matrix, well, updating A can't capture that. Okay, so what we show is that the error does decrease by some fraction of the maximum possible. Okay. And this is sort of independent of the sketching that you use. So obviously, depending on the type of sketching you use, you have to select a different number of samples. Like if you use uniform sampling, you may have to select more. If you use leverage score sampling, you can get away with selecting less, but estimating the leverage scores is expensive. In all of our experiments, we just did uniform sampling. Okay, so what's the intuition on how to choose the sketching rate? So I can tell you exactly how to choose the sketching rate if I knew the residual and the system matrix, and I did some computation that's expensive on them, okay? But we can't do that in practice, right? That would defeat the purpose of trying to use sketching in the first place. But the intuition is just like with SGD, at the start of your iterations, you don't need a very good estimate of your gradient. As you're getting close to optimum, you need to get a much better estimate of your gradient. So it's the same thing here. At the start, I can perturb the geometry of the system a lot with sketching, so I can sample a very small number of constraints. But as I get closer to convergence, to continue making progress, I need to sample more and more of the system. Okay, so with those pieces together, what we're able to say is if you choose the sketching rates based on this oracle that has that behavior, then we get an approximate critical point after T iterations with some probability, okay? So, this is the guarantee that we get. It's first sort of guarantee. It's not necessarily the best, but it shows that we do converge. In practice, this bears out as well. Unlike prior algorithms, which kind of stagnated because they use a fixed sketching rate, this does seem to continue converging. Okay, but again, that sketching rate is chosen according to some oracle that we don't have access to. So in practice, how do we select the sketching rate? Well, the key observation here is that this is an iterative process. So we think if we track the performance of different sketching rates over time carefully, then we should be able to hone in on the one that's performing best in the next step. Okay, so we're going to use an online approach. And because we're explicitly tracking the performance of every arm, we can track exactly what we care about, which is that we want to make as much decrease as possible in our objective in as little time as possible. So this is, when this thing here is large or small, I guess, I forget. When it's large or small, one or the other, this means that that's a good sketching rate, okay? And obviously we can't compute this for each sketching rate at every iteration, because that would be more expensive than just directly solving the system without doing any sort of dimensionality reduction. So what we do is at each time step, we flip a coin. If it comes up heads, then we update all of these statistics. If not, we use the statistics from the last time they were updated. Okay, so you use that coin to balance, sort of amortize the cost of updating these statistics over time. And then at every iteration, we select the arms with probability proportional to these weights. Okay, so here is an example of using this algorithm versus standard CPD ALS. So that's the blue line here is standard CPD ALS. Here we're plotting the relative error. And we look at different numbers of sketching rates here. And we see like this blue or purple line, I guess. This is if you have 5 arms, you can see it's doing a good job, or if you have 10 arms, it's doing a good job. Even up to 100 arms, this is still doing a good job of conversion faster than standard ALS. Okay. And then here is an example of taking a decomposition of a standard data set. It's a park bench video. So paraslice is standard ALS. Paraslice++ from prior work is ALS with a fixed sketching rate. And here we chose the sketching rate by running all of the same sketching rates that we do in our adaptive algorithm and choosing the one that performed best in hindsight. Okay, so this is actually giving this a lot of advantage. And you can see that even accounting for the sort of standard deviations, this algorithm gives us a lower error and faster. Okay. And of course, these standard deviations are larger because there's more randomness in the algorithm. All right, so moving on. If there's any questions on this, I can answer them now. No. Okay, so that's one application of sketching. And that's an iterative application, right? So we can get as much accuracy as we want. Now we're going to look at a one-shot application of sketching. This is very different than the sketching we saw before, but it sort of demonstrates the flexibility of these ideas. So here we're going to consider kernel k-means clustering. Okay, so we've all seen clustering before. The idea is we have some d-dimensional vectors and we want to cluster them into some number of clusters, let's say k. And the output of this clustering algorithm is going to be a label on each of these points that says which cluster it's in. And you can think of this equivalently as you're partitioning your numbers from 1 to n into k disjoint sets, right? So their union is the numbers from 1 to n and they don't overlap. Okay, so we've all seen k-means clustering before, probably. Okay. And the goal of k-means clustering is to minimize this sort of variance within a cluster from the cluster centroid. So I want to find a partition that minimizes this score here. So we can reformulate this as a sort of linear algebraic-ish problem by using this idea of a cluster indicator matrix. So let's say that I give you an arbitrary partition of the numbers 1 to n. Then I can define this cluster indicator matrix in this way. So it has as many columns as there are clusters. So in this case, I'm clustering the points 1 through 12, or the numbers 1 through 12, into 3 clusters, right? So there's 3 columns in my cluster indicator matrix. And then for each point I, if it's in cluster J, then the ijth entry of my matrix is going to look like 1 over the square root of the number of points in that cluster. So notice by taking this square root, I end up with every column of this matrix having length 1. And they're orthogonal to each other because the supports are disjoint. So this is a orthonormal, or a matrix of orthonormal columns. Okay, and there's this 1-to-1 correspondence between these cluster indicator matrices and partitions. Any questions on that? Okay, so that means that we can reformulate k-means in this way. So if you look at what this is doing, this thing here is really computing the centroids of my clusters, and then, comparing the distance between every point in a cluster from the centroid of the cluster. But this is nice because this is a projection matrix. So we've reformulated this k-means objective into minimizing over a non-convex set of projection matrices. So we know that k-means is NP hard, so we're going to assume we have some approximation algorithm for solving this. So they exist, right? They're not necessarily efficient, sort of. We can get a log k approximation efficiently. So here's an example of k-means clustering. Okay, in this case, our data looks sort of already clustered. So let's say running Lloyd's algorithm will quickly give us back a reasonable clustering. But now, again, we care about nonlinear clustering. So as you can imagine, in this case, Lloyd's algorithm is going to fail because these things don't look like sort of isotropic Gaussian clusters. So here's the output of Lloyd's algorithm if I ask it to find two clusters. So this is not useful. So we want to have a data adaptive way of clustering to get nonlinear clusters. So the idea here is that we assume that there's some nonlinear mapping, call it our feature map, that takes the original points and maps them into some space where k-means will do a good job of clustering them. Okay, so it should convert this arbitrary sort of cluster structure to something that looks isotropic Gaussian. Okay, the other thing we'll notice that's useful is that the sort of geometry of this problem really only depends on the inner products between these points. Okay, so if we look back here, our objective, this Frobenius norm, can be written in terms of inner products between points. Okay, so we really don't care that much about the nonlinear mappings themselves. We care about the inner products of the nonlinear mappings. And so we get this n by n matrix that maps all the points into this nonlinear space and takes their inner products. So this is our kernel matrix. And we can write our kernel matrix in this way, where the rows of this matrix consist of our points mapped into this nonlinear space. The important thing to note is that for standard kernel matrices, like our kernel choices, so this kernel function here, for standard choices of that, this actually has an infinite number of features. So we can't work directly with this matrix. Okay, so instead, what we do for kernel k-means, we'd like to cluster on these nonlinear features, but they may have an infinite number of columns. You can't really do that. Well, it turns out, you can check the linear algebra. Since phi transpose gives us k, this is equivalent to solving this, where I replace phi by the square root of k, or kernel matrix. It's a positive matrix, so it has a square root. Okay, we can get that from the SVD. Okay, so the key point here is that kernel k-means is going to be standard k-means over the rows of the square root of my kernel matrix. And again, we have this nice formulation as we're optimizing over some non-convex set of projections. Okay, so here's an example. So you see they're more separable with k-means here. All right, let's look at the computational costs. First, we have to form the kernel matrix. That's expensive. It's order n squared. Second, we have to take our decomposition. That's expensive. It's n cubed. And then we do Lloyd's algorithm. It's n squared k. So this is going to be impractical if n is large. So let's speed it up with sketching. We're going to use a particular type of sketching called the Nystrom method. So what the Nystrom method does is it selects a subset of your data point. So let's say this is my kernel matrix. I'll select a subset of the columns, and then I'll say that this kernel matrix should be well approximated by the span of those columns. So this makes sense, for instance, if your kernel matrix is low rank, then you would think if it's rank R, maybe sampling R columns or 2R columns and projecting onto that will capture most of what's going on into the matrix. Now this is symmetric, so that means that K should be well approximated as being in both, its row space should be in the span of C and its column space should also be in the span of C transpose. So we get this particular decomposition. Nice thing is we really need to compare all of our endpoints only to C other points. C here is the number of landmark points, the number of columns we select. So we reduce from this n squared computation to n times C to approximate our kernel matrix. So here is the idea of using Nystrom for kernel k-means. First, we take our Nystrom approximation that only requires n times C comparisons. And then to reduce the cost of Lloyd's algorithm, instead of working with n-dimensional points, we're going to work with s-dimensional points. So we truncate ks, we truncate k, or our low rank approximation of k, so that it's a rank S matrix. so that the nonlinear representation of each point only uses S features instead of N. Okay, so that's our B here is our feature matrix. And then we cluster using the rows of B as the representation of our points. Okay, so this is a guarantee on the clustering we get out of this. So remember, this is our objective function that measures how good our clustering is. So what we show is if we cluster using the representation given by B as opposed to the representation given by K itself, then we get a 1 plus epsilon plus some other factor approximation, okay? And so this tells us how small S can be. Remember, instead of using an n-dimensional representation of our points, we want to use an s-dimensional representation. Well, it turns out if we want K clusters, S needs to be on the order of K. And the larger it is, the smaller this factor gets, okay? But S is what we get after doing our dimensionality reduction on the Nystrom. So the Nystrom approximation itself needs to use more than S sample points, landmark points. And this tells us exactly how many we need if we want this epsilon approximation factor. Okay, so this significantly reduces the cost of doing nonlinear clustering. So I'll skip the sketch of the proof. Sort of the key point here is that there's this nice property that this truncated rank Nystrom approximation has, which is that it doesn't matter what orthogonal matrix I look at, I can approximate this projection using the projection on B. So that's the key point in showing that you're able to get a good clustering by using this rank restricted Nystrom approximation. Okay, and then you can look at performance versus another algorithm, spectral clustering algorithm that uses dimensionality reduction. Sort of the key point here, we're using both of these methods with the same bandwidth, and you can see that our algorithm outperforms the spectral clustering algorithm. Plus it's principled. The spectral clustering algorithm is not principled. You can get like complex numbers out of that.
What's the y-axis?
The y-axis here is the normalized mutual information between the recovered clusters and the true underlying clusters. So the higher it is, the better.
So are you also using Nystrom for the spectral clustering method?
Yes.
As well?
Yes, and that's why it's not principled, because when you compute the degrees, you can get negative numbers, so you end up with some complex numbers.
You can do Nystrom where you still keep the symmetry in the matrix, so it should be Hermitian. You get real value eigenvalues.
So it's not the eigenvalues, it's you approximate the degree. I think when you're taking the Laplacian, you need to approximate the degree as well, and that can be negative.
It's not usually how I've seen Nystrom. Like usually Nystrom can give the top eigenvectors for the graph. Laplacian, I've never seen complex numbers shown here.
Let's see, it's been a while. So you need to compute.
It's like a low rank.
Oh, I think this is the version that adjusts based on the degrees. So it's not the raw Laplacian, right? You like normalized by the degree of each normalization. Yeah. So that's, I mean, that performs better in practice if you did it exactly, but it becomes like a heuristic that doesn't. Even this problem, you don't run into it often, but it is a potential problem.
It seems like you're not doing it properly for getting complex numbers out of Nystrom, but maybe I don't understand.
Maybe we can talk offline. Yeah. All right. So that's the application to clustering, and then we can also apply the same ideas to another machine learning problem, which is ridge regression. So again, we're in a kernelized setting. Here we want to do kernelized ridge regression. So you end up with this, you're basically trying to do regression over nonlinear features and kernelize it. So you're working with the kernel matrix instead. And you want to solve this in the case where the kernel matrix can't fit in memory, because n here is like 1 million. So it's 1 million by 1 million, can't fit it in memory. So since the solution doesn't fit in memory, we're going to use iterative methods like conjugate gradient or Gauss-Seidel. In our case, we're considering Gauss-Seidel. So we're going to use a randomized block Gauss-Seidel. So at every iteration, we pick a subset of size p, right? So p is much smaller than n, and we do coordinate descent on that subset of features. In this case, we call it J. Okay, so there's two reasonable schemes for sampling. So one is you fix the partition ahead of time. So you partition all of your n features into blocks of p. You keep those fixed and then ahead of time, and every iteration you randomly choose which of those you'll use. The other is at each iteration, you randomly select a subset of size p. Okay, so the fixed partitioning is preferable just from speed, but the random coordinates, or if you randomly select your partition at every iteration, you might expect to make more progress, right? Because you're kind of mixing the coordinates more. So you can ask, what's sort of the difference that you can see? So you can come up with sort of, what do you call them? Just symbolic examples where you can compare the rate of convergence. But I'll skip that and just show here sort of empirically the difference. So if you use random coordinates here, you can see your relative error is going down much faster than if we used a fixed partition. And that's basically because if you think of this as preconditioning, you're using like a fixed block diagonal preconditioner in this case, and then in this case, you're randomizing that preconditioner, so you're mixing more. Okay, so to understand why this behavior differs, you can look at the analysis of randomized Gauss-Seidel. It has a linear rate of convergence where sort of the condition number is controlled by this number here. So this is the projection onto the square, that should be a K, projection onto the square root of our matrix multiplied by the sampling that we're using, okay? And in this case, the sampling matrix is very structured because it corresponds to this fixed partition. Okay, like I said, you can you can just analytically show that there's a big gap between these two methods. Okay, again, there's this trade-off. From the system's perspective, you prefer the fixed partition. From the optimization, you prefer random. Okay, we could ask what happens when you add acceleration. So we're gonna add Nesterov acceleration to these iterates. So then there's two questions. Does the same sampling phenomenon occur with acceleration? Like, is there still that gap? And then do we also get this square root of mu rate of convergence? Okay. So the behavior of the accelerated fixed partition sampling is already understood. We get this P over N factor times that rate of convergence that we saw before. And our main result is showing that if you use accelerated block Gauss-Seidel with any sort of non-degenerate sampling scheme, then you have this rate of convergence, okay? And this is tight. So there does exist a starting point where this matches this rate up to constants. So this rate here is given again by that same sort of condition number we saw before that depends on the sampling scheme. And then this new factor here, which behaves roughly like that N over P. Okay, but this holds for any sort of block sampling scheme, not just the fixed one, not just the accelerated one. It also applies to like Kazmarks. Okay, so what we were able to show is that this square root of P over N loss is real for the fixed partition scheme. So because that result characterizing the convergence is tight. And then for the random coordinate sampling, we were able to show that if our matrix is well conditioned in the sense that all of its diagonal blocks are well conditioned, then we'll get back a rate of convergence that looks like P over N times that condition number. Okay, so here is a large scale experiment on CFAR 10, kernel ridge regression. So you have about 250,000 points. And here we're sampling subsets of size 10,000. And you can see how the accelerated random partition works versus the accelerated fixed partition. and, you know, non-accelerated versions of those. So you do see a big gain with accelerating the randomized partitioning. Okay, so that's it. You can look at the same thing with respect to time, because remember, we're worried about whether the trade-off that you get in terms of optimization would be dominated by the loss that you get in terms of computation. So you see that the gap narrows, but it's still worth it to do the accelerated random partitioning. Okay. All right, that's it. If you have any questions, I'm happy to take them.
Back at the beginning, you said like one of the things about uniform sampling was the row coherence mattered.
Yes.
Is there like any intuitive understanding of row coherence? Is
Yes.
it something like the rank of the matrix or?
So it measures, so the coherence sort of measures how much there is a data point that's not in the span of the other data points. So for example, if you have a matrix that looks like the first row is 1, 0, 0, and then all the other rows are in a space that's, you know, orthogonal, then that matrix will have maximum coherence, because unless you sample that first row, you're going to miss something in the row space of that matrix.
Okay, thank you.
And that's why it controls the number of samples you need with uniform sampling. So basically, you could think of leverage score sampling as avoiding that issue by the probability of sampling that first row would be very high. Yes.
Question, could you like also like sketch lasso or something? Does this
Yes.
what people do? Yeah.
Yes, it is something people do. And yeah, it's a good idea.
Same kinds of results hold, or I guess there's something
I don't know.
different.
I don't know. I actually have a student now who's trying to do this for tensor, like the tensor setup, where we want structure on the factors. And in his case, it doesn't work well for whatever reason. For whatever we've been trying for tensors isn't working well. But there's papers where people have done it for standardless. Yeah. Yes.
What would be some things to look out for that would say, my problem would benefit from sketching, or my problem would not benefit from sketching?
Mhm.
Like some things that you would say, these are notable things to look for.
Yeah. So there's kind of two sort of broad ways to use sketching that you've seen here. One is sketch and get the solution straight out. Like that's what we did in the nonlinear case. And then you saw a bunch of iterative, well, not a bunch, saw two iterative algorithms that use sketching. I would say for the iterative algorithms, it can be very reasonable, right? There's not too much you need to assume really. If you have some sort of, basically you just need to have something that looks sort of over constrained, or, you know, have a lot of redundancy in it. And then you can sort of reach whatever accuracy you want by carefully tuning that sketching. If you're gonna do the one-shot sketch and use the solution, then your problem needs to have a lot more structure in it. So something like you're getting a low rank approximation of a matrix, that kind of thing that you know is low rank.
Other quick question would be, in terms of the rate of sampling, like a lot of methods in optimization for step size, I already have like a pre-computed sort of like, this is my plan, how I'm gonna do step size.
Yes.
Do you guys have any work that says like, here's my pre-computed plan for how I will do the sketching, and here's a convergence result like for that?
No, so you mean like they diverge, but they're square sum?
Yeah, something like that.
No. I think part of that is because these are randomized algorithms too, so it's a little, I mean, like if you look at my analysis, we used a union bound there. So an interesting question would be, can you give some sort of rate of convergence that holds, you know, without using a union bound, that takes into account that your error can sort of go up stochastically, but it should come back down. It's not really clear to me that there is some fixed step size schedule that would work. I feel like it should need to be adaptive. I don't know.
Thank
you.
So this seems like very interesting and great results, and there have been a lot of progress in sketching, and I'm just kind of curious, what's the vision for future in this area, because so much has been done in the area, so.
So I would say adaptive sketching. So you want to use sort of historical information to choose your sketching rate in the future. So, I mean, sort of all the linear algebra, I say this, but I'm sure, you know, tomorrow there'll be a new paper, but I feel like when I think about what are interesting problems, all the sort of straightforward applications of sketching are already there, right? So like lasso, for instance. So I'm more interested in, if you have this embedded inside of some optimization process, how can you choose your sketching there sort of well? So I think like Mark Palanchi and Rachel Ward, those kinds of people, I think are looking at that stuff as well.
For the dynamical systems, or?
Dynamical systems, just like changing your sketching rate adaptively. Yeah, I don't know anyone, I mean, I guess maybe Gunnar Martinson is doing stuff with dynamical systems.
Yeah, thank you.
Mhm.
Thanks a lot.